Here are some notes and an example problem for Boyle's law. Boyle's law tells us that volume and pressure are inversely proportional to each other for a fixed mass of gas at a constant temperature. Here are your equations to express that. You can express it this way: volume equals K times 1 over pressure. And you can just do a little bit of algebra to rejigger that into this form: pressure times volume equals K. What's K? K is a constant. So if you take that fixed mass of gas, let's say it's 20 grams of oxygen, no matter how you alter the volume of that gas, no matter how you alter the pressure on that gas, when you multiply its pressure times its volume, it's always going to equal the same thing, and we call that K. Well, what does that mean for us for being able to calculate what the new volume will be or what the new pressure will be? Well, this is how we do it. So your initial pressure and your initial volume, we'll call that P1 and V1, multiply them together, you're going to get that constant, K. When you alter one of those, the pressure or your volume, you're going to alter the other one too. So your final pressures and volumes are your P2, your V2, multiply them together, you're going to get that same K. So your first pressure times your first volume is going to equal your second pressure times your second volume. P1 times V1 equals P2 times V2. It does not matter what units your pressure is in or what units your volume is in, as long as you keep that consistent on both sides of your equation. If your V1 is in milliliters, this will give you a V2 in milliliters. If your V2 is in liters, it'll work as long as your V1 is in liters. Same for pressure. Any units for pressure are fine as long as you got the same ones on both sides. Let's look at some of those units for pressure you might see. Here they are. Pascal. It is the SI unit for pressure. It is the same as Newton per meter squared. You might also see pressure expressed in millimeters of mercury. That is the pressure that supports a millimeter of mercury in a column, in like a glass barometer. So think about that experiment we read about. If you've got a glass tube turned upside down so the opening is in a pool of mercury, it'll drop down that tube a little bit and have a vacuum at the top, but air pressure on that pool of mercury will support some mercury in that column. So if you increase the pressure enough to raise the mercury in that tube by 1 millimeter, you've increased your pressure by 1 millimeter of mercury. A torr is exactly the same as a millimeter of mercury. Pressure is also measured in atmospheres. An atmosphere is just the amount of pressure that the Earth's atmosphere exerts at sea level at a temperature of 0 degrees. If you convert atmospheres into millimeters of mercury in your barometer, it's the same as 760 millimeters of mercury, which is the same as 760 torr. It is also the same as 101.325 kilopascals. Not pascals, kilopascals. So that means 1,000 pascals. So multiply this times 1,000 to convert it into regular pascals. So you might see your pressure measurements in any of these forms. All right, let's do one. Here's your example problem. You've got a balloon with a volume of 4.5 liters. It's floating high in the atmosphere, and the pressure up there is 57.03 kilopascals. What's the volume of the balloon going to become if you take it all the way down to sea level? Assume that temperature stays constant at 0 degrees. All right, well, we know our formula for solving changes in pressure or volume according to Boyle's law. P1 times V1 equals P2 times V2. All right, what are our values for these? P1, our starting pressure. We know that it is floating in the atmosphere where the pressure is 57.03 kilopascals. What's our V1? What's our starting volume for our balloon? It tells us 4.5 liters. 4.5 liters. All right, what's our P2? We do know our final pressure because we know it is going to be brought down to sea level, and we know what the pressure is at sea level. Look at that previous sheet of paper. At sea level, at 0 degrees, the pressure is 1 atmosphere. and 1 atmosphere is the same as 101.325 kilopascals. Our P1 is given in kilopascals, so we want our P2 to be in that same unit, kilopascals. So let's take this, 101.325. Oops, I already have an equal sign there. P2 equals 101.325 kPa. Our volume, at the end, our final volume, our V2, we don't know. That's what it's asking. What will the volume of it become if we bring it down to sea level? If the question asked you, like, what will the volume of it become if it is brought down to a level where the atmospheric pressure is 75 kilopascals? And that would be your P2. That's 75, because that's what it's telling you the pressure is that you're bringing that balloon to. But it tells us we bring it to sea level, and because of that previous sheet of paper, we know how many kilopascals of pressure are present at sea level. All right, let's set it up. Sorry for the shadow. All right, P1 times V1 equals P2 times V2. Here's our P1, 57.03 kPa, times our V1. Here's our V1, 4.5 liters, equals P2 times V2. Here's our P2, 101.325 kPa, times our V2. That's what we're looking for. That's what we don't know. All right, do a little bit of algebra here. We want to solve for V2, so we should divide each side by 101.325 kPa. I'll go ahead and write this out long form, 57.03 kPa times 4.5 liters divided by 101.325 kPa equals our V2. All right, kPa cancels since it's on the top and the bottom. We'll do our arithmetic, 57.03 times 4.5 divided by 101.325. I did the arithmetic already. Will be 2.533. The only units that we have left are liters, equals our V2. And that is our final answer. So if you take that balloon that's floating so high in the sky that the pressure up there is only 57.03 kilopascals, it's 4.5 liters of volume. You bring it down to sea level, it's going to shrink the volume of that balloon down to 2.533 liters. That's your V2.